Okay, so it's 10 o'clock, so we are going to start. Yeah. So welcome, everyone. So I would like to introduce IFISC PhD student Juan Ignacio de Gregorio Masiota, who will present today his thesis entitled An Information-Theoretic Approach to Higher-Order Markov Processes, Theory and Applications. I would like also to introduce the committee members forming the panel that will evaluate the thesis. On my left is Professor Salvatore Michiche from Università di Palermo in Italy. On my right, Massimiliano Zanin from IFISC. And here, myself, I'm Marta Sales Pardo from Universitat Rovira i Virgili. And well, you know the rules. You have an hour, and once you're done, we'll ask you some questions. I will ask if anybody in the audience wants to leave, then they will be allowed to do so. One more thing, please do not clap, neither at the end of the talk nor at the end of the questions. You can clap once the whole thing is done and we already tell you our final decision on the evaluation. And I think that's all from my side. So the floor is yours.
Perfect. So, well, thank you everybody for coming, and thank you for the introduction. So let's begin with a quick outline of my talk. I will start by introducing the general background and motivation for my talk. I will then define a little bit what stochastic processes are, and in particular higher order Markov processes. Then I will define some tools that would be important from information theory. And then I will go to the main results of my thesis, in particular to a connection we found between these higher order Markov processes and information theory. This will lead us to explore the issue of entropy estimation. I will then explain a method we developed to estimate the order or memory of this high order Markov chain. And then I will explain some applications we did of all of these tools to two real-world datasets, in particular weather and linguistic data. And I will finish with some conclusions and an outlook. So the general topic of my thesis was the analysis of stochastic processes. This is a framework to model systems that evolve over time due to random factors. And here the focus is on the probabilities of transitioning from one state to another over time. So this has an overall simplifying effect because we do not need to know the exact details of how this process works. We just need to worry about these transition probabilities. And also, these processes are useful because randomness and uncertainty are inherent in most real-world scenarios. And also, stochastic processes have a wide range of applications in complex systems, going from biology to human and animal mobility, linguistics, weather, and so on. So let's stop for a little bit in this last example of the weather. So we know that a day can be either rainy or sunny. And let's suppose that we know that today and yesterday were rainy, which seems pretty accurate here in Spain. And we would like to know what is the probability that tomorrow will be sunny. Well, we can do this a number of different ways. So for example, we could calculate the probability of tomorrow being sunny with no regard about what happened the previous days. Or we can do it by taking into account that today is rainy, but forgetting about whatever happened before. Or we can do it by taking into account that both today were rainy. So I think it's more or less intuitive to see that these probabilities do not necessarily have to be the same. And also, in general, well, the more previous outcomes we consider, well, it will be better in general. But the question is, can we stop at some point? And this is the main question that motivated the first part of my thesis. So given some stochastic process, if we want to predict its evolution, do we really get more information the more and more previous outcomes we consider? Maybe we just need to consider a finite number of past outcomes, because knowing a larger history will not tell us anything new. So in order to answer that question, we need to analyze temporal correlations in a process, or in other words, we need to analyze how previous outcomes affect the evolution of the process. So now, talking a little bit more general, let's consider a random variable x with L possible outcomes, these betas. So in the weather case, the possible outcomes are true, rainy or sunny, or the variable could be a coin flip, in which case we also have a binary system with outcomes heads and tails, or the variable could be the nucleotides in a DNA, in which case the possible outcomes are 4. Now, for each state of this variable, we have a certain probability of occurrence. So, for example, in a fair coin, we know that the probabilities of heads and tails are both equal to a half. Now, if we repeat this random variable over time, we basically have an stochastic process where the time can be either continuous or discrete, but here we will only consider the discrete case. So in the weather example, time is represented by the days, and also these possible outcomes can also be continuous or discrete. But once again, here we will only worry about the discrete and finite case. And also, we will only consider stationary processes in which the probabilities remain unchanged over time. Now, some definitions that will be useful for the rest of the talk. So besides of wanting to know the probability of each outcome in a random process, we want to compute the probabilities of consecutive repetitions of the variable. And to these groups of R consecutive repetitions of the process, we call it blocks of size R, or R-grams. And sometimes we will notice in this more compact form, like beta R, sometimes in its more extended form, depending on the context. And so in the weather case, for example, the blocks of size 2 represent all the possible states that the weather can be in 2 consecutive days. So for example, yesterday and today rainy, or yesterday rainy and today sunny, and so on. We will also work with the transition probabilities of order U, which tell us the probabilities that the process will be in a certain state at time U plus 1, given that it was in a sequence of states in the previous U time steps. And as I said before, we want to analyze temporal correlations in a process. And we say that a process has first order correlations if, taking into consideration the previous outcome, tell us something new about the probability of the next outcome. So in the weather case, we'll say, for example, that it has first order correlations if knowing that today is rainy changes the probability that tomorrow will be sunny. And in more general, we say that a process has youth order correlations if the youth previous outcome tell us something new about the evolution of the process. Now, some processes do not present temporal correlations at all. These are usually called independent identically distributed, or IID processes. The most common example here is probably a coin flip, in which the probabilities of heads and tails are always equal to a half, no matter what happened at any other previous time step. Some other processes have only first order correlations. These are known as Markov processes. And here the probability of a future outcome depends only on the current state of the system. Now, more general, we say that a process or a Markov process has memory or order M if it has only up to mth order correlations, in which case the transition probabilities satisfy this relation, which in other words, it means that in order to predict the evolution of the process, we only need to consider the m previous outcomes, because knowing a larger history will not give us any additional information. And here, well, the m equals 0 corresponds to the IID case, and m equals 1 to the Markovian case. So here at the top, I show you a graphical representation of a memory 1 process or a Markovian process, in which, for example, the outcome at time s depends only on the outcome at time s minus 1. And here it's a sketch of a process with memory 2, in which the outcome at time s depends on both the outcomes at time s minus 1 and s minus 2. So now we can reframe our original motivation within this framework by asking these questions. How can we quantify correlations in a stochastic process, and how can we determine its memory value? And for that, we will use information theory as our main tool. In particular, we will work with the Shannon entropy, which is a measure of the uncertainty or diversity of a random variable, and it has this very well-known definition. And in particular, we will work with an extension of this concept, which we call block entropy, which is basically Shannon's definition, but instead of considering only the probabilities of single outcomes, we will consider the probabilities of consecutive repetitions of the variable. And well, we define here H0 to be 0. It can be seen that H1 is equal to the Shannon entropy, and this is why we call this an extension. And it's also bounded like this. Now, we'll also work with the Kullback-Leibler divergence, which is a measure of the difference between two probability distributions. And also, we will work with the discrete derivatives of the block entropy. So in particular, the first derivative can be shown to take this expression, which in the limit, it's equal to the entropy rate, which is an important quantity in information theory, as it measures the uncertainty in the next state of the process, given the entire past. And also, we will work with the negative second derivative of the block entropy, which we call predictability gain, and it takes this expression. And I will talk a little bit more about this quantity in a couple of minutes. So I started saying that I wanted to analyze, quantify correlations and memory effects in stochastic processes. And now I'm talking about information theory and entropy. Well, why? Because there is a connection between these concepts. In particular, there is a theorem we proved that says that a stochastic process has memory M if and only if the block entropy is linear for block sizes bigger or equal to M. This has some corollaries. So for example, for a process with memory M, the entropy rate takes this form without the need to take any limits. And also the predictability gain is equal to 0 for all values bigger or equal to the memory. So here, for example, I show you the plots of a process with memory 3, where we can see that all of these properties are satisfied. So for example, the block entropy becomes a linear at r equals to 3. The first derivative becomes a constant at r equal to 3, to a value that corresponds to the entropy rate. And also the predictability gain goes to 0 at u equals 3 and remains at 0. So this means that we can redefine the memory of a process completely in terms of information theory. In particular, we can define it as the minimum eta, such that the predictability gain is equal to 0 for all values bigger or equal than eta. And also, there are some interesting properties about this predictability gain that we proved. So for example, it can be shown to take this expression in terms of the Kullback-Leibler divergence. So here we can see that predictability gain represents the average amount of information gain when considering u+1 instead of uth order transition probabilities. This is basically why we call it predictability gain. It's also bounded like this. It's also additive. So if we want to compute the information gain going from uth to kth order transitions, well, we can compute it as the information gain going from u to u+1, plus u+1 to u+2, and so on. Also, the total predictability gain takes this form, which is the difference between the Shannon entropy, the normal entropy, and the entropy rate. So this is the total information gain when going from a description that does not take correlations into account to one that takes the full history of the process into account. And also, for a process with memory M, this predictability gain at M-1 is a measure of how far the process is from actually having memory M-1. So for all of these nice properties, we propose that the predictability gain is a good candidate for answering our questions, which were basically analyzing and quantifying correlations in stochastic processes and for determining its memory value. However, so far we have considered that all the probabilities and the entropy are exactly known, but in a real case, this is not what happens. In a real case, we only have access to some data, and we need to estimate all of these quantities using this data. And in particular, we propose here to estimate the predictability gain using its relation to the block entropy, simply because entropy and entropy estimation is a very well-studied subject in the literature, and there are many entropy estimators. So we can now add a new question: which entropy estimator to use? And for that, we need to compare them for correlated sequences. So we need to talk a little bit about entropy estimation. And before that, I will talk a little bit about numerical estimation in general. So suppose we are given a sequence of observations S, which is obtained from n repetitions of a random variable, and we want to estimate a certain quantity A using an estimator, which we will notice as this hat A. So for example, let's suppose that we want to estimate the probability of one of these blocks of size R. So for that, we can group our sequence in overlapping blocks of size R, count the number of times the block appears in the sequence, and divide it by the total number of blocks in the sequence. So let's suppose that we observe the weather 10 consecutive days, and we obtain this sequence. So from here, we could estimate the probability of observing a rainy day, and it would be 0.6 in this case. And we can also calculate the probability of having 2 consecutive rainy days, which in this case would be 2/9. So in general, given some estimator, we want to know how good it is, in a sense of how well it approximates the real quantity. For that, we can take into account some statistics, for example, the bias of an estimator, which measures the difference between the average value of the estimator and the real quantity. And we say that the estimator is unbiased if this bias is equal to 0, which is, for example, the case of the probability estimator I showed you before. Also, we want to know the standard deviation of an estimator, which measures its dispersion. And if we want to take into account both of these statistics into a single value, we can define the mean square error as the sum of the square of the bias and the standard deviation. So for an estimator, what we want is for all of these quantities to be as close to 0 as possible. Observe here that all of these statistics involve the calculations of these moments of A, which is defined as this, where this sum runs over all possible sequences of size n. And here, the probability of observing a particular sequence, well, it depends on the correlations in the process. For example, if the process is IID, then this probability is simply the product of the probabilities of each outcome. But if the process is Markovian, then the probability of observing a particular sequence, well, it involves the first-order correlations. So we can see that the moments of the estimator and therefore its performance depends on the correlations in the data. Now, talking a little bit about entropy estimation in particular, well, it is well known that there is no unbiased estimator for this quantity. Also, that this bias is more significant in the undersample regime, which occurs when the data sample is smaller than the number of possible outcomes. And since we are interested in estimating block entropy and the number of possible blocks grows exponentially with the block size, if we let this value increase, then eventually we will reach the undersample regime. So that's a problem. So as I've said before, there are plenty of entropy estimators in the literature. Here we only consider these ones, which I won't go into the detail of each one, don't worry. I will just mention that this maximum likelihood estimator is probably the most common one and is simply obtained by replacing the exact probabilities by the estimated probabilities in the formula for the entropy. And also, I would like to mention this geometric estimator, which even though it was already known, here we gave it a new interpretation, and we also showed that its bias is always less than the biases of these two estimators for IID sequences. Now, all of these estimators have some things in common. So, for example, they are all constructed considering independent sequence, that in the sense that, for example, all permutations of our data will provide the same result, and they are mostly analyzed and compared only for IID sequences, even though, as I argued before, the performance of an estimator usually depends on the correlations in the data. So, in my thesis, we proposed a new approach, which is to construct estimators that take into account these correlations, in the sense that, for example, permutations of our data can provide different results. So the first estimator we proposed, we call it correlation coverage adjusted estimator, or CC, which basically makes two corrections to the definition of the entropy. One is an adjustment to account for missing elements in a finite sequence, and the other one is a correction to the probabilities that is calculated sequentially by taking into account previously observed data. And the second estimator we proposed, we call it corrected Miller-Maddow, or CMM, and it basically makes a correction to the bias of this maximum likelihood estimator by considering the first-order transition probabilities. So then we wanted to compare the performance of our new estimator with the old ones in two Markovian cases, one binary sequences and the other in an undersample regime. So let's go first to the case of the binary Markovian sequences. Here, the possible outcomes, we call them 0 and 1. And these processes are basically defined by these two transition probabilities. And here I'm showing you the absolute bias of 4 estimators when applied to sequences of length 4 and for different choices of the transition probabilities. Here I'm showing only 4 estimators, basically because of lack of space, but we did it for all the estimators. And well, here the colors imply lower biases. And we can see that well, all estimators have different regions where the absolute bias is the lowest. But for all of them, they have the same region when the bias is highest, which is around this corner, where both transition probabilities are very close to 1, which is a very particular case. And then we wanted to do the same, but for the standard deviation. Here, in contrast to the bias case, we see that all estimators have the same regions where sigma is lowest and highest. In particular, the standard deviation is highest around this L-shaped region in all of them. However, it's a bit difficult to draw general conclusions about the performance of the estimators by considering these color maps. In particular, because here we are only considering one sample size, and we would like to see how the estimators behave for different sample sizes. So for that, we defined these aggregated values, which are similar to average value. Now here I'm showing you the aggregated bias, deviation, and mean square error of all of the estimators as functions of the sample size. And here particular attention should be made to the red and black curves because they are our new estimators. And we can see that both of them managed to reduce the bias in almost all cases, but they present quite large deviation when compared to other estimators. And when taking both quantities into account in the mean square error, we see that the ones with lowest value are these NSV and BHM estimators. And then we wanted to compare the estimators in a Markovian undersample regime, where here we consider 64 possible outcomes, these betas, that obey these transition probabilities, which may seem a bit weird, but we showed that this is equivalent to the dynamics of the blocks. And since we want to estimate block entropy, then it makes sense to consider a process of this form. So here I show you the bias and standard deviation of all of the estimators when applied to sequences of size 20 as function of this parameter P, where, well, here the most important conclusion we can see is that the red curve, our CC estimator, well, it manages to reduce the bias quite a lot for all values of P. However, once again, it presents quite a large dispersion. And the CMM estimator, the black curve, has the opposite behavior. It has quite large bias, but quite a small standard deviation. So once again, we wanted to compare these estimators for more than one sample size. So we define again these aggregated values in a similar manner to what we did with the binary case. And here, again, I show you the aggregated bias, deviation, and mean square error of the estimators as functions of the sample size. Well, again, we observe the same behavior, that the CC estimator, the red curve, presents quite a small bias, but quite large deviation. And again, when taking into consideration both of these statistics, we see that the one with lowest mean square error is actually this NSB estimator. So what did we learn from all of this comparison? Well, that our two new estimators manage to reduce the bias when estimating entropy for Markovian sequences. However, they present large deviation compared to other estimators. And overall, we found that it was this NSB estimator, the one that presented best behavior. So this is the estimator we will use moving forward. However, although this estimator has nice properties, we still want to avoid estimating the entropy in undersample regimes, basically because here all estimators work poorly. So this means there is a maximum block size up to which we can reliably estimate the block entropy. And here we take this maximum value to be this one. So going back to our motivation, we now have a way of quantifying correlations in a process from data by using the relation between the predictability gain and the block entropy and using this NSB estimator. But now, if you remember, we also wanted to estimate the memory of a process, and earlier we defined it to be this minimum eta such that the predictability gain is equal to 0 for all values bigger or equal to eta. Now here you may wonder, as we did, is if we really need this very strong condition that it has to be 0 for all of these values. And the answer is yes, because there are some processes that can have zeros in the predictability gain before reaching its memory. For example, I show you here two systems with memory 6, where in the first case, where actually the predictability gain is non-zero only at u equals 5, and this other case where the predictability gain is 0 kind of periodically until reaching u equals 6. So yes, in a general case, we do need to consider all values of the predictability gain when trying to estimate the memory of a process. However, as I argued before, we can reliably estimate the predictability gain only up to a certain maximum value. And this is something we basically have to live with. And also, given the statistical errors that come from estimating stuff from data, we cannot simply reject a trial memory eta if the estimated predictability gain is non-zero for some value. A more careful approach is to compare the predictability gain of our data with the predictability gain of sequences that we know have memory eta. And we can do this with the technique of bootstrapping, which is a very well-known method in statistics. And here it involves estimating the eth order transition probabilities from our data. Using these transition probabilities, we can generate sequences that we know by construction have memory eta. And then we can calculate p-values by comparing the estimated predictability gain of these numerical sequences with the estimated predictability gain of our original data. Notice, however, that in hypothesis testing, when the hypothesis involves only one p-value, this is usually compared to a critical value alpha, where this alpha is related to the error committed. But here, for the hypothesis that the process has memory eta, we are calculating more than one p-value, all of them, actually. And if we compare each one to alpha, then our total error committed will be larger than alpha, and in particular, it will be larger than this value. So there are different strategies to deal with this. Here, what we did was combined all of these p-values into a single one using Fisher's method, where the combined p-value can be calculated like this as function of this product of the p-value we want to combine. And then we can compare this combined p-value with our critical value. So overall, with all of these techniques, we developed our predictability gain, or PG, memory estimator, which is basically the minimum eta for which we accept the hypothesis that our data has memory eta. And then, well, we wanted to compare the performance of our estimator with two of the most widely used estimators in the literature, which are the AIC and BIC. And here we compare them for binary sequences of different lengths and memories going from 0 to 4. So here, for example, for sequences of length 100 that have memory 0, well, 95% of the time, using our approach, we will correctly guess that these sequences have memory 0. And for AIC, it's only 42%, and BIC, it's only 83%. So overall, from this table, we can see that pretty much for all cases, our PG estimator has a higher accuracy. And in some cases, this accuracy this improvement is quite large. So what have we done so far? Now, given some sequence, we have a way of quantifying temporal correlations using the predictability gain. We have a way of estimating the memory of a process using this PG estimator, which has some advantages. For example, it's independent of model selection in contrast to methods like AIC and BIC. It provides a better description of the process because it does not only tell you the memory, but also it can quantify correlations. Also, it may alert us if our data is actually not compatible with a high-order Markov process, because in that case, all these combined p-values would be smaller than the critical value. And as I showed you before, this PG estimator has a higher accuracy than AIC and BIC, at least for binary sequences. So what we want now is to use all of these tools into real-world applications, in particular for weather and linguistic data. So first application, weather data. And for this, we can go back to our original example of the weather. And here, what we wanted is to analyze correlations in precipitation sequences. So for that, we took the data from here. We consider only Spanish stations, which were approximately 170. And we took data spanning 30 years, where each day for each location, we classified it as rainy or sunny. And we wanted to analyze the correlations for different stations and different months. So here, I show you the predictability gain of these precipitation sequences for a station in Madrid, where, for example, we can observe that in May, well, our data corresponds very well to a Markov process, to a memory 1 process. But for the same station in January, well, this is actually not enough. We have to consider that the sequences have memory 2. So we can see that even for the same location, we have different correlations and different memory values for different times of the year. So then we wanted to analyze this more generally. So we estimated the memory of these precipitation sequences for all stations and all months. And for example, here we observe that 78% of the stations in January have memory 1. From this table, we can also see that during summer months, there is an increase in stations with memory 0. And during winter, there seems to be a slight increase in sequences with memory 2. So apart from wanting to estimate the memory of these sequences, we also wanted to analyze correlation. So for that, in this box plot, I show you the distributions of the estimated predictability gain at 0 for each month, where we can see that during summer months, there is a clear decrease in correlation. And for the rest of the months, well, these distributions seem quite similar. And then we wanted to analyze how these correlations vary geographically. So for that, we calculated the average predictability gain for all stations in winter and in summer. And here, well, the more red the colors mean a stronger correlation. And we can see that in both seasons, the strongest correlations appear around the region of Galicia. And also during winter, well, in the central region of Spain, there seems to be higher correlations than regions like Catalonia or the Balearic Island. But in summer, well, all of these regions have quite similar correlations, very close to 0. So that's all for the precipitation data. Now let's go to our second application of linguistic data. And for that, we wanted to analyze correlations in syntactic sequences, which then can allow us to define and quantify distances between languages and to explore the correlation between linguistic and geographic distances. So by syntax, I basically mean how languages structure their sentences. And for that, we consider these parts of speech, which are the categories of words that have similar grammatical properties. Here we consider 15 of these categories, which are basically adjective, verb, noun, and these kind of things. And we took the data from the universal dependency libraries, where texts from different sources are converted into this part of speech sequences. So for example, the sentence, the red book, is converted to the sequence determiner adjective noun. So we can work directly with these syntactic sequences. And here in this work, we consider 67, mostly European and Asian contemporary languages. So as I said before, we wanted to first analyze correlations into syntactic sequences for different languages. So here I show you the estimated predictability gain of 4 of these languages, where we can see that all of them have a decreasing pattern. However, when trying to estimate their memory using our PG estimator, well, we observe that actually a Markov model from 0 to 3 is not compatible with our data. This suggests that these sequences have a memory larger than 3. However, we can still gain some insights by looking at these curves. So for example, in all cases, the estimated predictability gain at u equals 2 and 3 is quite low, especially when compared to the values at u equals 0 and 1. So this suggests that actually transition probabilities beyond order 2 do not provide additional significant information in these processes. So in other words, we can consider that this process have memory 2, and this could be a quite good approximation. So And this implies that, well, the syntactic structure of languages is mostly captured by the blocks of 3 consecutive parts of speech, or trigrams. So using this idea, we can define a distance between 2 languages by calculating the distances between the trigram probability distribution. And here, in particular, we use the Jensen-Shannon distance, which is a well-known metric that fulfills all the properties of a distance. And it's also bounded between 0 and 1. So here I show you the trigram probability distributions of English and Japanese. Well, for example, we can see that the most probable trigram in English, it's at position determiner noun, whereas for Japanese, it would be noun at position noun. So from these histograms and with the Jensen-Shannon metric, we would get that the distance between these 2 languages is 0.79, which is quite large. So then we did this exact same procedure for all language pairs in our analysis, and we obtained this distance matrix, where here darker color mean smaller distances. And well, a lot can be said about this matrix, but I don't have much time, so I just mention some highlights. That, for example, we can see some clusters formation, like this one, which correspond to Slavic languages. Here, this more dense cluster are Romance languages. Here, this kind of large cluster are mostly Indo-European languages. Here, this smaller cluster is composed mostly of agglutinative languages, which is a special type of language. So, well, overall, we can see that our results make sense, which is always good. And then we wanted to analyze the correlation between linguistic and geographic distances. So for that, we are, for each language, we assign a geographic location, and we calculated linguistic and geographic distances relative to all other languages. Here I show you 4 examples for 4 languages, where with the x-axis here is in logarithmic scale. So from the Pearson coefficients and the p-values obtained, we can see that there seems to be a logarithmic relation between these 2 distances. And interestingly, we observed that the Basque language was the only one that presented a significant negative correlation. And then we wanted to analyze how these 2 distances are related more generally. So here we plot all distance pairs in our, and here, well, we computed different correlation coefficient, this distance correlation coefficient, which is more general than Pearson's. And once again, from the value and the p-value obtained, we can observe that there is indeed a significant correlation between these 2 distances. And well, that's basically all for the results. So now some conclusions. So in my thesis, I showed that correlations in stochastic processes can be quantified with information theory. In particular, I show you that the memory of a high-order Markov chain corresponds to the block size from which the block entropy grows linearly. Also, this means that we can define the memory in terms of the predictability gain, which was the negative second derivative of the block entropy. This, in order to quantify this value from data, we first needed to analyze entropy estimation in Markovian sequences. And for that, we introduced 2 new estimators, which were designed to take into account correlations. We observed that although they managed to reduce bias, they presented quite large dispersion compared to other estimators. So overall, we observed that it was the NSV estimator, the one that showed the best performance. And then using these techniques with techniques from hypothesis testing, we developed a memory estimator that showed high accuracy. And then we wanted to apply all of these tools in 2 real-world datasets. The first one was to analyze precipitation sequence correlations in precipitation sequences in Spain, where we observed that there are stronger correlations in winter than in summer. and also that there are stronger correlations in North Spain compared to the rest of the country. And the second application involved the analysis of correlations in syntactic sequences in languages, where here we observe that the syntactic information is mostly contained in parts of speech trigrams. This allowed us to define and quantify distances between languages and to analyze correlation between linguistic and geographic distances. So our work leaves some questions open or opportunities for extensions. So, for example, all the theoretical results I'll show you in the first part were done considering only stationary processes. So it would be interesting to account for non-stationary effects. Also, it would be nice to compare the performance of entropy estimators for sequences with memory larger than 1. Also, to develop estimators for the predictability gain that do not involve estimating the block entropies. And also, if you remember, our PG memory estimator involved two parameters. One was this alpha, which was the critical value to which we compare the p-values, and the other one was the number of resampling we did. So it would be nice to find optimal values for these parameters. And even nicer would be to find distribution of the estimated predictability gain so that we could calculate these p-values more efficiently without the need to do the resampling, which can be computationally expensive. Also, regarding the precipitation analysis, one could consider larger number of categories because we only consider a day to be rainy or sunny, but this could, of course, be extended. And regarding the linguistic analysis, it would be interesting to consider more syntactic features, not only parts of speech, and to separate the data according to the source. So, for example, news or literature or speech and written text to see how correlations are affected or not by these changes. So, thank you all for your attention. Thank you to my supervisors. Thank you to the jury. Gracias a mi familia que están ahí despiertos. That's all.
No, thank you very much. So now we're going to start with the questions, but before that, if anybody wants to leave, and please feel free to do so.